Modern generative AI models process an enormous volume of data. Every time a user uploads a massive document, pastes an entire codebase, or engages in a long-term conversation, the context window absorbs tens of thousands of individual tokens. To process this data without continuously recalculating the same inputs from scratch, the system relies on a high-speed memory structure known as the key value, or KV, cache. It acts as a temporary digital cheat sheet for the neural network. This diagram of an H100 GPU shows the scaling problem. The model weights take up a small fraction of the VRAM, but for a single session using a Llama 3.18b model with a 128,000 token context window, that massive block representing the KV cache alone demands 16 gigabytes of memory. That single user's 16 gigabyte footprint monopolizes a significant portion of a high-end enterprise GPU, locking the system before a second concurrent user session can even begin. Hardware manufacturers and cloud providers are finding that physical memory capacity, rather than raw computational processing power, is the primary constraint on high-concurrency AI deployment. This animated diagram shows a side-by-side comparison of standard data quantization. To solve the memory limit, engineers typically map continuous 16-bit floating point values into smaller, discrete integer buckets, like a 4-bit or 3-bit space. Shrinking the data this aggressively introduces severe rounding errors. At the 3-bit level, these micro-errors compound. They diverge wildly from the original values, destroying attention accuracy and causing the model to lose semantic coherence or hallucinate. To avoid significant accuracy loss, traditional quantizers require quantization constants, a layer of high-precision metadata that specifies how to rescale each block of integers back into floating point values during inference. Storing this full precision metadata alongside every small block of data adds 1 to 2 extra bits per number. At ultra-low precisions, this overhead mathematically negates the intended memory savings. Researchers at Google have developed an alternative algorithm called TurboQuant. By utilizing multi-dimensional rotation and 1-bit unbiased estimators, it bypasses codebook metadata entirely, compressing KV caches down to an effective 3.125 bits per element. Scaling long context inference requires treating data compression not as a sorting problem reliant on massive lookup tables, but as an exercise in manipulating mathematical geometry. Older vector databases required analyzing entire datasets offline to build custom compression codebooks. TurboQuant operates entirely online during live inference. It is strictly data-oblivious. Polar Quant ingests 16-bit vectors, multiplying them by a random orthogonal matrix. This rotation whitens the messy data into a uniform Gaussian distribution centered at 0. The system then converts Cartesian coordinates to polar, separating the vector's magnitude from its angular direction. Because these rotated angular distributions are highly concentrated and statistically predictable, the system can completely bypass the expensive per-block normalization step. An optimal 3-bit scalar quantizer handles the base compression across all channels instantly without generating a single byte of metadata overhead. By forcing irregular data into a predictable shape, Polar Quant secures extreme base memory reduction without the fatal overhead penalty of traditional codebooks. Forcing precise 16-bit values into a 3-bit space inherently leaves behind tiny numerical deviations. This is the residual quantization error. Standard compressors treat this leftover deviation as acceptable noise. TurboQuant isolates this specific micro-error to prevent it from compounding inside the neural network. The architecture routes this to a second component, the QJL transform. It projects the residual error into a lower dimensional space, forcibly reducing each resultant value to a single binary sign bit, +1 or -1. When the language model computes an attention inner product, this stored sign bit acts as an active correction mechanism. It counteracts directional bias, mathematically canceling out the systematic error introduced by the 3-bit base compression. TurboQuant does not discard the mathematical error left behind. It weaponizes that exact error as an unbiased estimator to yield accurate attention calculations at a fraction of the memory footprint. Mathematical viability depends entirely on infrastructure alignment. For an algorithmic compression scheme to work in production, it must map perfectly to modern hardware. early implementations lacking hardware-level vectorization attempted to unpack this multidimensional matrix math via simple Python loops. That approach introduced a 63-millisecond processing overhead per prefill phase. Bypassing this latency required specialized engineering. Google developers authored custom Triton CUDA kernels designed specifically for fused dequantization directly on the GPU's tensor cores. These kernels execute a highly vectorized bit packing architecture. They pack exactly 32 1-bit QJL sign indicators into a single INT32 container. This density allows the system to combine the 3-bit quantized base index with the 1-bit contribution from the QJL layer. The final effective memory footprint equates to exactly 3.125 bits per element. TurboQuant trades the developmental simplicity of rapid integer truncation for complex kernel engineering. It demands specialized programming to maintain execution speed while achieving theoretical optimality. The theoretical pipeline translates directly into measurable empirical performance on modern hardware accelerators, specifically the Nvidia H100. This split-screen visualization shows the dual operational gains. The Triton kernels compute attention logits up to 8 times faster than unquantized baselines, while simultaneously reducing the required KV cache VRAM footprint by a factor of 6. For enterprise adopters, the primary concern with extreme compression is the potential degradation of contextual accuracy during complex retrieval scenarios. In rigorous needle-in-a-haystack validation tasks utilizing the Qwen 3.5 architecture across 64,200 tokens, a 3.5-bit precision implementation of TurboQuant maintained a 100% exact match rate. Maintaining a perfect retrieval score at 3.5 bits demonstrates that the systematic error correction of the QJL layer is sufficient to preserve the semantic integrity of the original 16-bit data. These operational metrics directly dictate financial utility. The primary beneficiaries are enterprise applications that require massive document intelligence, codebase analysis, and multi-turn autonomous agent workflows. In unoptimized systems, a standard retrieval augmented generation workflow referencing heavy internal compliance manuals rapidly devours 25 gigabytes of VRAM per individual session. TurboQuant compresses that exact requirement to roughly 4 gigabytes. A single 80-gigabyte hardware accelerator can suddenly host an exponential multitude of concurrent analytical agents. The strategic caveat lies in deployment architecture. Executing this algorithm without incurring severe processing latency heavily favors environments locked exclusively into the Nvidia CUDA and Google software stack. This geometric approach to multidimensional data provides an immediate expansion of serving capacity, extracting utility from current generation silicon that hardware manufacturers cannot yet provide through physical memory density alone.